Good evening and welcome everybody, this is Obi-Wan Pez for Simplex Pachinko. So glad that alert went off. Apparently Firefox was eating too many of my resources, so it needed to go away. Oh, goodness. Let's do a quick snap refresh, just to make sure. No, wait, never mind. Nope, never mind. I was gonna say let's do a snap refresh, but my Firefox is now closed, so that doesn't help. Or my Firefox is now open, so that's not a good idea. And there we go. All right. Hope everybody's doing all right. This whatever day it is, Wednesday. Yes, Wednesday. I was thinking about streaming last night, but then Don was on and he was doing a good job, so I'm like, let's just hang out in the audience. Okay. So for tonight, if anybody has any questions on mathematics, feel free to drop them in chat, and I will get to them as soon as I can. Have our tablet that we can write stuff on. And if nobody has any particular questions, I'm probably just going to keep going on with differential equations, or maybe pull a analysis book from this pile over here. I don't know, we'll see how it goes. How's everybody feeling? I had something over in the corner that was using like 81 gigs of virtual RAM. Like, that's not a no. Good. Let's go and reset the canvas. Go back to small and blue. Just got word our shipment of home goods has left Hamburg and is currently on its way to, I think, Portsmouth, England, where it will go through the vital inspection process by customs, and who knows how long it'll be until it actually gets here. But they said June, it's the middle of May. One can hope. I'd really like it to get here soon, because sitting on the floor is very difficult to maintain circulation in my feet. It's pretty fun though. Every so often I just lay myself down on the floor and I can just hear my back go like all the way along it. It's great. Oh. And it looks like somebody, probably me, put a wet glass on top of my tablet. Anyway. So yeah, hope you're all doing well tonight. Let's see what I got. I got partial differential equations. We could do that. That's kind of fun. We have our analysis book by G.H. Hardy. Sure. See what happens here. At least I don't think I've started on this one. Been working on a project recently. Got interested in attempting to like start some notes on writing something. I am not a good writer by any means, but at the very least, I would not be the person with the if it does turn out to be even remotely good, it could be picked up by somebody who is a much better writer, so. Alright, so... Real variables we get here, rational numbers. And Hardy says rational numbers are going to be represented by R equals P over Q. We know this from other examples. I've done this plenty of times on the channel and talked with various people about how to construct rational numbers and what rational numbers really are. Where P and Q can be any integers we want, provided that we know the usual restriction Q is equal to 0 will be eliminated. This backslash that's given here, and yes, this is a backslash. People are reading URLs out loud. This is a backslash. Going forward is just a slash. So https://. Those are forward slashes because they're leaning forward. I will be picky about this. Welcome on in, everybody. If you are new here, my name is Obi-Wan Pez. This is N-Simplex Pachinko. And if you are here for math help, please drop it in chat, and I will get to you as soon as I can. And commonly, P and Q have no common factor other than 1. So we call this relatively prime. So numbers like 12 and that was a mistake. And 49, for example, are relatively prime to each other, whereas neither of them are actually prime numbers. 12 and 140, or no, 12 and 49 don't have any common factors other than 1. So they are relatively prime to each other. Okay, to the rational numbers, thus defined, right? Rational numbers 0 can also be collected by saying, okay, let P equal 0. Okay. He also suggests that maybe it would be better to just say, like, well, Q can always be positive, and therefore we eliminate this whole issue of if we let Q belong to the strictly positive integers, then P can just belong to all integers, and we don't have any sort of restrictions. We don't have to worry about Q being 0. We don't have to worry about, like, oh no, what do we do when we have positives and negatives? Hardy just says, okay, well, if we state this, we can also do this because P over negative Q is equal to negative P over positive Q, and negative P over negative Q is just equal to P over Q by itself. So it doesn't really matter where we put the negatives, as long as we doesn't matter where we put negative numbers. As long as we're clear with our definitions, this is just kind of the easiest way to define rational numbers. So let Q just be positive integers only, and then P can be any integer we want. Alright, example 1, if R and S are rational numbers, then R plus S, R minus S, R times S, and R over S are also going to be rational numbers, except when S, the denominator, is equal to 0, in which case it doesn't work in the first place. So and I have a note here from one of the original owners. Who is it? I wonder. I kind of wonder if I can tell from the handwriting, but probably not. I believe the original owner was Frank Mizellevich from Philadelphia. Most likely either a math engineering or a physics student at, I don't know, let's see, Cumberland Street in Philadelphia. What school is on Cumberland Street in Philadelphia? East or west? Well, it does actually say, I believe it's west. Search area for university. Oh, you know what? It's Temple. Yep. That makes sense. I want to say the guy that I got it from also went to Temple, so I don't actually know that 100%, but you know. Or I've seen some other books, I think, that were stamped with Temple. Don't believe he taught there, but I'm pretty sure he... The black pads came out of the bottom of my keyboard. Hooray, sticky. Okay, so I have a note, probably from the original. Substitute fractional values for R and S. Yeah, so this is the basic way to show closure, as we would call it now. They must have back then too, but nope, other way around. So we're going to show closure for the rationals. Under each basic operation. Okay, so R and S are both going to be rational numbers. And again, the way we define them is that R is going to be P over Q, and S is going to be PQ RS damn M and N. This is perfect, yes, 100%. No flaws, no notes. Alright, so the way we show closure under each of the basic operations is we say, okay, these are what those are going to be. They are PQMN, PQ, you know what, wait, let's go with the other definition that Hardy gives us. So P and M will be any integer, and Q and N will be any positive, strictly positive integer. And again, this is going to boil down to the same this is going to boil down to the same argument, where we can get non-unique rationals by saying Q and N can be any integers we want, as long as they're not 0. So we don't have to particularly say that, oh no, this one has to be, these two have to be integers and these two have to be positive integers. It doesn't really matter. We're just saying it's all equivalent, and it's just easier if we ignore the potential for the denominator to be 0 in the first place, because if we don't have that, then we don't have to worry about it. And all the other ones are equivalent anyway, so it's all good. Okay, so what does closure mean? That means that if... Oh, okay. All right. Closure means that if... nope. If A and B belong to a particular set S, then doing some sort of operation, A star B, is also going to be under S. And this is a generic operator, not multiplication. Which I know is confusing because I use it all the time, but I use that star for specifically multiplication all the time. If you were to say... Snowflake. That's a terrible looking, I don't even know what that is. Kraken? Miniature Kraken? Right, there was a good... we used one of these times, I don't remember what it is now. but whatever. Generic operator. So we don't know exactly what it is. I think usually it's called a binary operator. At least in this case, right? Because it's taking two things in, doing something to it. Okay, so we're going to show that this does actually hold for those particular numbers. So we already know that this is going to work because we've seen what happens when you add two fractions together. You get either a fraction or a whole number, and a whole number is just another fraction. Right? We've never seen anything weird happen or anything different happen. So we just have to say, yes, this will in fact happen for literally any of our rational numbers. So first of all, we have to establish that integers are closed under addition, subtraction, and multiplication. See, just did it. Addition, subtraction, and multiplication. Integers are not closed under division, because when you take the integers and you take two random integers like 5 and 7 and you put them into a fraction with each other, or you divide them 5 over 7, that is no longer an integer. So we're not able to divide integers and get another integer, at least always. We could do it sometimes, obviously. 14 over 2, for example, is just 7 over 1 or 7. So that's an integer, but again, 5/7 or something like that will not be. So it all depends on what you pick. We're just trying to say, yes, it will always happen one way or the other. Okay, so R plus S is going to be equal to P over Q plus M over N, which is going to be equal to, here we can multiply our first one by the missing part of the fraction that we need, and same with the second one. First one requires an N in the denominator, second one requires a Q. Now, in theory, these could also have common factors, and so it could be pared down a bit. They don't have to be relatively prime to each other. However, this method will always work. If you multiply by n over n to the first fraction and q over q to the second fraction, then both of them end up with an nq in the denominator. Again, might not be simplified, but who cares? This is going to work for us. So we get this. We get now Pn over nq. And yes, if we multiply it this particular way as shown, it's going to be Qn, but right, multiplication with integers is also commutative, so we can just flip them around to make it slightly easier to work with. All right, mq over nq is equal to Pn plus mq over nq. Okay, now all of this stuff in the numerator is going to be an integer, and all this stuff in the denominator is going to be an integer. So now this is saying that this new thing that we've created is now of the form nuts. Is now of the form, haven't used a and b, so is of the form a over b, where a is an integer and b is a positive integer. Is that necessarily true? N and q were both positive integers, so the denominator is going to be a positive integer. Yep. So we could even go back and say, yeah, that one's going to be strictly positive. So this means that a over b is going to be a member of the rationals. Therefore, r plus s is going to be a member of the rationals. All right, there's one. All right, r minus s is going to be equal to, well, this is going to be the same thing. So this is going to be p over q minus m over n. And again, we can multiply by n over n and q over q, respectively. Okay, this is eventually going to work itself out to be Pn minus mq over nq. And once again, our numerator is all going to be integers. Our denominator is going to be strictly positive integers, and therefore this will be of the form a over b, where, again, this fraction is now going to be a rational. Okay, so that means that for the second one, our subtraction is going to be r minus s is going to be also a rational. Check. Arg. All right, r times s is going to be p over q times m over n, which is going to be equal to pm over nq. And again, p and m might be positive or negative, don't know. So this is going to be, at the very least, just an integer. And nq is going to be a strictly positive integer, just like every other time. So therefore, this is going to be of the same form, a over b, where, no, a over b is going to be an integer, nope, is going to be rational, there we go. Therefore, r times s is going to be a rational number. Okay, and then we have r over s. So this is going to be p over q divided by m over n. So now what? Phobos! So, like, we're not allowed to just say that, oh, well, yes, clearly, this is part of, we're checking closure, so we're not allowed to say, well, this is closed because the division yields this stuff. We don't know. Currently, this is a rational number divided by a rational number. We don't know if it is a rational number itself. So we have to check that. So by doing this, we're going to have to say, let's take top and bottom, multiply by top and bottom by q, top and bottom by n, and this will make sure that our denominators, the compound denominators, go away. Okay, so that means that up top here we're going to have q's dividing out, and then we get pn. And at the bottom we've got mq. our n's multiply away. Okay, so this is where it gets potentially a little weird, but p times n could be any any integer. P could be any integer, and n must be strictly positive. So, don't know exactly. Right? Oh, and we did have the one condition here. S was not 0. So, therefore, m cannot be 0. Okay, so our numerator has to be an integer. Our denominator also just has to be an integer. And we said in this case, just without 0. Q was already defined as not being 0. And in this particular case, S cannot be 0, therefore M cannot be 0. So that works that bit out. Yeah, so we already said Q and N cannot be 0 itself. N in this case doesn't actually come into play. It's just going to be up top. And we said before that with all this stuff, our Pn over Mq, if one part of it is negative, then that's just going to be like, oh, well, the other part can be negative as well. Or, again, if it was negative Pn over negative Mq, then we could simplify that to just Pn over Mq. Okay, so because of that, what we've just shown is that we're going to get something of this form, one way or the other, right? We just move the negative part up top if that ends up, if the denominator ends up being negative, and then we can trade both of them, right, to divide out a -1 from both top and bottom if they're a common factor. So then in this case, we're going to end up with Pn up top and MQ down bottom. Essentially what we're doing is we're saying, okay, well, this is going to be an absolute value. And then our top one, we don't know. This is potentially plus or minus Pn, depending on what MQ was in the first place. Not the point, though, right? That's ridiculous. Anyway, so in this particular case, we now show that our P over Q ended up... that was weird. Our P over Q divided by our M over N is equivalent to Pn over Mq, which again are closed under integer multiplication, and then the whole thing is now an integer divided by another integer. Again, denominator can't be 0, so therefore we end up with something of the form a over b, which is then going to be a rational number. Therefore, R over S is also a rational number. If you don't like it, please let me know, and we can always try to explain it a different way. Hey Zach, how's it going? And just so as you all know, right? Zach took time out of his day to end up making everybody a, you can spell, make everybody who participated in our real analysis class woohoo! Certificate of completion. Thank you so much. Let's go! I'll hang it in the back somewhere when I actually get my desk in. Oh, you know what? I should probably... I know, right? So it's regular U.S. mail, and I was just like, you know, it's gonna get here when it gets here. But I mean, we've got military like all over the place around here. So, and I don't just mean England. I mean, you know, Europe in general. There's a bunch of military personnel, so their letters are coming over, and you know, I mean, like I told you, Zach, it doesn't matter when it gets here. It'll just U.S. mail gets here when it gets here. I'm not too worried about it. But yeah, they've been really fast. I think there's got to be at least a once weekly air shipment that's just coming over. Also, possibly when they get a full bag, they just toss it onto a passenger plane or something, and you know, give them whatever money they need to make the journey. There we go. All right. My monitor got like 40 seconds behind. That was fun. So yeah, tonight we were just doing some stuff out of the G.H. Hardy book. I really should not open and close this too much because the whole front of it is starting to shear. And every time I open it, there's a little bit more. There's a little bit more bookbinding, like in the crease. All right. So that is exercise 1, or example 1. Whatever, it's fine. So example 2 says if lambda, m, and n are positive rational numbers, and m is greater than n, then, oh boy, lambda times m squared minus nn squared to lambda mn and lambda times m squared plus n squared are going to be positive rational numbers. i.e., show how to determine any number of right-angled triangles, the lengths of whose sides are all rational. Yikes. I mean, it's not hard, it's just kind of like, I guess that's how we're saying it now. Okay, so let lambda be a over b, m be c over d, and n be e over f. With that introduction, then lambda times m squared minus n squared is going to be equal to a over b multiplied by c over d parentheses squared minus right, e over f parentheses squared. I mean, like, using example 1, we showed that subtraction and multiplication are, but that just proves they're rational. Okay, now we gotta prove that they're also positive. If we do this and say that this is going to be greater than 0, then one of the things that we can do... Yeah, I mean... Yes. And we know how much I like being pedantic, so that's the other potential problem here. One of the ways that we can do it, like uncovering wise, oops, that's not it. Okay, I don't want to do it there. It's a bad idea. We can multiply both sides of the inequality by b over a. Algebraically speaking, this allows us to say, okay, well, we're going to uncover, this is the multiplicative inverse of a over b, therefore we can be left with a positive 1 on that side, and then we're multiplying 0 by any number, it's going to be 0. And we know that a over b was positive, so therefore our inequalities, that doesn't change at all. Nothing weird happens there. I mean... It's also fair. I mean, it's true. And it does lend itself to slightly less algebra, at least algebraic manipulation. If we multiply first one by f squared over f squared, then we end up with cf over df parentheses squared minus second one by d squared over d squared, so de over df parentheses squared right, a over b cf squared minus de squared over df squared. Assert it's greater than 0. Right, so you pull a little lemma over on the side. And like you said, Zach, right, so m is greater than n, therefore c over d is greater than e over f. And the other part of this one up here. was that A, B, C, D, E, and F all will be positive integers. Again, without loss of generality, they could all be negative, but like, again, we're just going to go with the simplest version of it. If they make positive rationals, we'll just say that all of them were positive integers themselves, and not worry about the possibility of all of them being negative and just dividing out, because that's silly. Vlog. Right, so yeah, I'm not over here yet. So in this particular case with the lemma, we can say that we do know that we're allowed to multiply by D and F on both sides. So yeah, CF is going to be greater than DE. And since everything is positive, CF minus, well, okay, we could do this. And then over here on the left, we could say that this is AB. Now, if we just want to, for instance, show that CF squared minus DE squared is also going to be greater than 0, we could do that pretty easily within the lemma. If we square both sides, and again, like you said, they're increasing functions, they're all positive in the first place, therefore it's going to form a one-to-one relationship, and it's just going to it will just be so. So CF squared will be greater than DE squared. There's another option, which is always fun. No, always. You say that this is going to be CF minus DE times CF plus DE. This is one of my favorite things that I always forget to do. It's still an option. You could still do this. Okay, so CF minus DE is going to be greater than 0. CF plus DE is going to be greater than 0. DF squared is going to be greater than 0. And A over B is going to be greater than 0. Yeah, I think I like this one slightly better just because I can show it directly from the lemma, and I don't have to make any, pseudo-ridiculous arguments or anything that somebody's going to be like, well, I don't know. There might be a case in which, and I'd have to explain the whole thing, what I just said, about, all of these things are positive integers, and therefore when we square things, we don't have to worry about it's going to be a strict magnitude increase when we square things. We don't have to worry about sign changes or anything like that. But with that, right, we could just say, all right, well, because of that cool stuff that we did, all of this stuff is greater than 0, and therefore, yes, it is true that lambda times m squared minus n squared is going to be greater than 0 by everything that we just established there. Cool. Yeah, I know. We didn't define increasing function. My daughter was slightly disappointed today. She had a substitute teacher in because her teacher is out with a different grade doing something else, and for math, she was doing geometry, which is the first time she has touched geometry other than, like, you know, just basic shapes. This is the first time that they've actually come up with, like, vocabulary words and things like that. And so the sub said something to the effect of, you know, how many vertices are on this particular shape? And a bunch of kids raised their hand, and my daughter was like, so I don't know what a vertice is. And the teacher said, well, I'm not stopping to answer that question because this is something that a second year should know. I was like, she said, what now? Excuse me? So I kind of want to know if she in particular, or the whole school in general, is accepting of that kind of behavior. Oh, fine. I mean, I guess technically this is a real analysis course book as well. Yeah, I have the certificate. You're allowed to do that. All right. Yeah. So I was just like, yeah, no, that's no. Define increasing already. That's fair. I mean, like I said, we defined it. Didn't define it in context of this book. I mean, to be fair, it's also something we do in Calc 1 and 2, so, you know, it's not like I would not begrudge them to be like, whoa, I don't know. Like 2 lambda m n. So, this one's a little ridiculous, right? Because, like, by example 1, we already know we already know 2 lambda mn is closed by multiplication, so therefore it. Oh, right, shoot. Right. Okay. So. Yeah, so, my daughter misspoke because she didn't know the right word, at least as far as I know, unless they do say vertice here. But I leaned back, I turned around to her in the car while we were stopped at a red light, and I was like, oh, you know, just so that you know, generally speaking, vertex, vertices, and, okay, so what's a vertex? I was like, yeah, all right, fair enough, but nonetheless, because she just thought I was, you know, saying something different, I guess. But then again, you know, this is England, so maybe they do use different words for what their stuff is. Okay, so by exercise 1, this stuff is going to be, it's closed under multiplication to get us the fact that it is a rational number, but we didn't say anything about the signs up there. So we also know that we don't want integers. Positive numbers. Closed under multiplication. But if we absolutely must, we can say, okay, well, positive integers will be closed under reals, or under multiplication, and then do the thing that we were doing up here, where we just say, okay, that's 2 times a over b times c over d times e over f both top and bottom end up getting us positive values, and therefore this whole thing, right, 2ACE over BDF, and again, both of these things will be part of the positive integers. Yeah, I know that. You know that. But she's 11, so I'll give her a pass. And again, American school, so we didn't exactly teach this, as far as I know. Alright, so with that, because of this, then we get to lambda mn belonging to the positive rationals. Cool. Alright, and then similar argument there, lambda times m squared plus n squared. I feel like he should have switched those. Have the students do lambda times m squared plus n squared first, show that this is positive rationals, and then do the minus case as like your last one. But yeah, directories. Directrices. Is it a multi-parabola? Right, so again, all this stuff is equal to A over B times the quantity, C over D parentheses squared, plus E over F parentheses squared is going to be equal to, again, we can do this all day if we want, C squared times F squared over D squared times F squared plus E squared times D squared over squared times D squared. And again, we assert that this is greater than 0, and then we just have to show it. Alright, CF parentheses squared plus DE parentheses squared over DF parentheses squared. And as above, so below. No, wait. All this stuff is going to be greater than 0. This addition here, since it's addition, it's going to be greater than 0. And this stuff down here is going to be greater than 0. So with that, this is now going to be positive. It's all going to be positive, and then we end up with something that, again, we're multiplying. It's going to be closed under multiplication and addition. The denominator is going to be closed under multiplication in terms of positive integers. And so the whole thing will end up being a member of those positive rationals. Alright. If anybody does have any questions on math, please drop it in chat and I will get to it. Right now we're doing some real analysis and just having a little bit of fun here with this extremely old book from 1928. Was it? Yeah. I gotta stop turning pages. I want to say I've seen this one before, but I don't remember how to do it. Example 3. Any terminated decimal represents a rational number whose denominator contains no factors other than 2 or 5, or mathematically inclusive. Conversely, any such rational may be expressed in one way only, as a terminated decimal. Well, so in this has got to be some sort of closure argument that we can use for this. Coffee away from the electronics. Okay. I mean, clearly, right? But okay, so how do we do this such that we can prove it for all rationals? Like I said, it must be like, I'm thinking it's some sort of closure argument, but what's the definition of a terminated decimal in the book? There isn't one, because this is on page 1. And it says here the general theory of decimals will be considered in Chapter 4. Chapter 4 starts on... Chapter 4 starts on page 106. That being said, right? Large values. I mean, that's limits. It's not actually talking about decimals. Easy, don't do that. Interpolation. So, I mean, this is going into like convergence and stuff like that. Representation of functions of a continuous real variable by means of limits. Things like that. Alternative proof of Weierstrass's theorem. Now, that's Chapter 4 is also where we start getting steadily increasing or decreasing functions. Yeah, even if it does have a common factor, right? It's gotta be some sort of power of 10 in the denominator. I mean, I like to keep it at essentially grad level, but alright, give me 1 minute here. Alright, we'll get rid of pre-roll while we're here. So, 3 minutes, get up, stretch, get water, stuff like that. Be right back. Alrighty, welcome back, everybody. Do-do-do. So yeah, we're looking at deciding how to do this. And you're right, Phobos, definitely. There needs to be, if it's a terminated decimal, there's a finite number of digits that can be represented by powers of 10. It's not exactly what you said, but close enough. Alright, so... Right, essentially we're going to get something that looks like... J. Okay, so we could do like an integer portion if we really wanted to. Oops. Hello. I'm not sure exactly where to put the stressors on your name, but Agent Ulsri, possibly. Let me know how you would like to be called. So, I mean, essentially we'd be looking at something like this, where we'd be saying that there's going to be all sorts of coefficients, which are going to be labeled a sub j, and then those are all going to be multiplied by 10 to the negative j. Do it in lean. Nice. Well, welcome. My name is Obi-Wan Pez. This is N Simplex Pachinko. We are, generally speaking, wanting to do mathy type stuff. And we also occasionally do game streams. Usually it's like 1 and 1 a week. Lately I've been trying to pick up a little bit more in the math sector, just because, you know, hardly anybody else does. So. That being said, we do have an awesome group of fellow streamers who are located right here. In order listed, we have Dawn Does Math, Zach, or E to the 2i Pi, who is here in chat tonight. We have Penn Center, Ian Stuckey, myself, Obi, Danny Highway, and Dr. Gold, who is Actual Education. All of us stream math at various points during the week, and feel free.